Hello, this is the problem solving session for waves at the beginning of the Waves and Optics unit. And before we get started on the actual problems, a broad comment about these wave problems. Many of them can be solved mostly with ideas that you bring in from Physics 1, especially ideas that you have about constant speed. So keep that in mind as you're working through these kinds of problems as well as the problems on the waves part of the homework. So the first problem is involving a wave, or I guess a wave pulse more correctly, at a sporting event. It reads, during sporting events with large densely packed stadiums, spectators will send a wave or a pulse around the stadium. As the wave reaches a group of spectators, they stand with a cheer and then sit. At any instant, the width W of the wave is the distance from the leading edge, people just about to stand over here, to the trailing edge where people are just sitting down. Suppose a human wave travels a distance of 853 seats around a stadium in 100 seconds, with spectators requiring about 1.8 seconds to respond to the wave's passage by standing and then sitting. So what are the wave speed V and the wave width W, both one in seats per second and the other in number of seats? Well, the wave speed V is simply going to be using ideas from Physics 1 that says speed is distance traveled over time. So the wave travels a distance of 853 seats. It takes 100 seconds to get around the stadium. So that is 8.53 seats per second. B is a little bit trickier. How wide is the wave? And you need to think about the motion of the wave during this part. So if this person is going to stand up and then take 1.8 seconds to stand up fully and then sit back down, the question really is how far will the wave have traveled in that time, because that will tell you what the width of this pulse is. And so B is simply taking that 8.53 seats per second speed that the wave is traveling this direction and multiplying it by the time that it takes a person to stand and then sit down as the wave is passing. And we find if we multiply those together, those are about 15.3 seats, which means that, the picture's not drawn accurately. There would be, on average, about 15 people standing up at any given time, though at the leading edge, they're just starting to stand up, and at the trailing edge, they're starting to sit down. Problem 2 actually has a geology connection. Those of you that have had a geology course might have studied seismic waves and the different types of waves that move through the Earth. When there's an earthquake or something as minor as a beetle walking, it reads, a sand scorpion can detect the motion of a nearby beetle, its prey, by the waves the motion sends along the sand surface. The waves are of two types, transverse waves that are traveling 50 meters a second and longitudinal waves traveling at 150 meters a second. If the sudden motion sends out such waves, the scorpion can tell the distance of the beetle from the difference in the arrival times of the waves at its nearest leg, leg nearest to the beetle. So if that time gap is 4 milliseconds, what is the beetle's distance? Again, from Physics 1, we know that speed is a distance traveled over a time, but we have two different speeds we're dealing with here. The transverse speed is the distance traveled, and that's just d from the beetle to the scorpion, over some amount of time, transverse time, that I'm denoting with a subscripted t there. And I also have the longitudinal wave travels same distance d, but it travels it in a shorter period of time since it gets there first. So I'm going to call that delta TL. But in both of those expressions, d is the same, which means I can set everything else equal to itself. So I can say the speed of the transverse wave times the time interval of the transverse wave equals the speed of the longitudinal wave times the time interval of the longitudinal wave. But the transverse wave takes 4 milliseconds longer than the longitudinal wave. So we could also write this as the velocity of the transverse wave times the time of the longitudinal wave plus that time difference of 4 milliseconds, though I'm going to leave things symbolic for the time being. So then if I put these things out and cluster them, I'll have velocity longitudinal times the time longitudinal equals the velocity transverse times the time longitudinal plus the velocity transverse times that time gap. If I solve for the longitudinal time and get both things over here, I'll have longitudinal speed minus transverse speed times the longitudinal time is equal to the transverse speed times the time difference. And solving for that longitudinal time, it's going to be the transverse speed times the time difference over the difference between those two speeds. Then we can go ahead and plug in numbers. So that's 50 meters a second. The time difference is 4 milliseconds. And I'm going to keep it in milliseconds, even though we generally convert units, because I got speed in the numerator and denominator, so those units are going to cancel out. Longitudinal wave's 150 meters a second. Transverse is 50 meters a second. So 50 divided by 100 is 1/2, which means the time for the longitudinal wave to arrive is 2 milliseconds. So what is the distance? Well, that's going to equal the speed of the longitudinal wave times the time of the longitudinal wave. 150 meters a second times 2 milliseconds gives you a distance of 30 centimeters or 0.3 meters that beetle is from the sand scorpion. Problems 3 and 4 deal with the relationship between wave speed, tension in the wave, and linear mass density of the wave. So in the book or in the lecture, we've seen that speed of a wave on a string or a wire or something one-dimensional like that is the square root of the tension in that string divided by the mass density. So the problem says the speed of a transverse wave on a string is 170 meters a second when the string tension is 120 newtons. To what value must the tension be changed to raise the wave speed to 180 meters a second? Well, some of you that play musical instruments might be aware that if you have, say, a guitar, the wavelength of the fundamental mode of oscillation of that guitar string is fixed because that's the length of the guitar neck. And if you want to raise the wave speed, what you're trying to do is increase the frequency of the tone, make it a higher pitched tone. So to make the wave move faster, I can tighten the string, increasing the tension. This question is just asking us how much must the tension be changed to raise the wave speed to 180 meters a second. Well, I'm going to rearrange this expression here to say that the square root of the mass density is the square root of the tension over the speed. And the mass density is the same in both of these situations. So I can actually write that this ratio in situation 1 equals this same ratio in situation 2. But since it's asking us for tension, I'm just going to go ahead and square both of these. So I could say T1 over V1 squared equals T2 over V2 squared, again, because the mass density is the same in the string. I haven't changed the string out. So I'm looking for the tension in scenario 2. That's going to be V2 over V1 quantity squared times the tension in string 1. If we plug in 180 meters per second, 170 meters per second squared times the 120 newtons, we find that the tension has to be increased to about 135 newtons in the string. Problem 4 that we looked at dealt with heavy and light strings. Those of you, again, who've played a stringed instrument know that the strings have different diameters, and some of the strings are therefore heavier and lighter than other strings. This is on a certain violin. They have linear densities of 3 grams per meter and 0.29 grams per meter. So what is the ratio of the diameter of the heaviest string to that of the lightest string, assuming that the strings are of the same material? The way this problem is written, it really just becomes a geometry question. But I've seen similar questions to this, and then they either tie to what tension the string has to be retuned to, or things of that nature. But really, we're just comparing two violin strings, and I'm going to exaggerate their dimensions here, shrinking them lengthwise and expanding them diameter-wise. But they're both going to be the same length if they're on the same violin. But string 1 has 1 diameter, and string 2's diameter is smaller. I know that the mass density of string 1 is 3 grams per meter, and the mass density of string 2 is 0.29 grams per meter. So if I want to know the ratio of the diameters, if I had, say, 1 meter of length here, that means string 1 is going to have a mass of 3 grams, and string 2 is going to have a mass of 0.29 grams. So really, how does the diameter relate to the mass of the string? Well, you actually have to bring something you learned in high school physical science to play here, and that density of any solid is that mass of the solid divided by the volume of a solid. And sometimes you see it written symbolically as such. And these strings are cylinders, so the volume of the cylinder is pi times half the diameter squared times the length. That's the whole volume of that. And since we're wanting to compare masses, let's go ahead and solve that for mass. Mass equals the density times pi times half the diameter squared times the length. Well, if you think about these, both these strings are going to have the same mass density because it said they're made of the same material. They don't have the same linear density, but they have the same overall density of the material. If they're both steel, steel has a fixed density. Well, I guess depending on the composition of steel. But if they're the same composition, pi is a constant, 2 is a constant, and they have the same length. So from this, we can really say that the mass is proportional to the square of the diameter. And if that's true, then we can set up a ratio and say the mass of string 1 to the mass of string 2 must be the same as the ratio of the diameter of string 1 squared to the diameter of string 2 squared. And if we're solving for the ratio of the diameters, that means the diameter of string 1 over the diameter of string 2 is the ratio of the square root of the mass of 1 to the mass of 2. Again, I'm just going to artificially select 1 meter lengths. It wouldn't matter what number I use here. So that ratio is the square root of 3 grams over 0.29 grams. And if we calculate that out, that ratio becomes approximately 3.2. Stringed instruments use the principle of standing waves when you're producing the tone on them. In problems 5 and 6, we're looking at standing waves, such as standing waves on a string. If you've done the lab prior to working through this session, you'll have observed some standing wave patterns and realized that when we're talking about standing waves on a string, we have 2 fixed ends, and so we have certain patterns of standing waves that can be produced. We're asked what are the lowest frequency, the second lowest frequency, and the third lowest frequency for standing waves on a wire that's 10 meters long, has a mass of 100 grams, and is stretched under a tension of 250 newtons. So I'm just going to make a little sketch. So if I have this string, the lowest frequency is when the string is vibrating back and forth in this fashion. I guess I didn't quite get it connected to the end there. The second lowest frequency is when you end up with a string that has 1 node in the middle. It's kind of like that. Third, the pattern keeps on repeating there, so now we go to having 2 nodes in the middle, and string shape something like this. Again, the string's oscillating back and forth except for these points at the nodes where it's not moving, but when we watch it overall, it looks something like this. So the lowest frequency is when I have this pattern, and if you extend this wave past here, you'd have to go 2 times this full length to get a full wavelength. So in this lowest mode, the wavelength of mode 1 is actually half of, whoops, let me do that again, 2 times the length of the gap that I've stretched that string over to get the full wavelength. So we want to know what the lowest frequency is. Well, we got to put together 2 ideas here. One is that wave speed is the square root of the tension divided by the mass density. And 2 is that wave speed equals frequency times wavelength. So if we put those together and solve for frequency, frequency is speed divided by wavelength. So that's the square root of the tension divided by the mass density divided by the wavelength of a particular mode. So the frequency of mode 1 is going to equal the square root of, okay, so let's see, tension, we have 250 newtons. Mass density, well, I have a mass of 100 grams, so that's 0.1 kilograms divided by the full length here, which is 10 meters for that string. And the wavelength, well, again, in this mode, the wavelength is going to be 20 meters because it's twice the length of that gap. And if you punch all that into a calculator, you come up with a lowest frequency of just under 8 hertz. Now you can actually repeat this calculation each time if you want to, but it's easier if you realize the pattern that emerges here. This is the lowest frequency, and to produce the second lowest frequency with the node in the middle, the wavelength is now equal to the full length of the gap rather than twice the length of the gap. So the wavelength's been cut in half. That means the frequency is doubled, and the frequency of mode 2 is going to be twice what it was here, or 15.8 hertz. Similar reasoning for 3. 3, now the wavelength is 2/3 of this gap. In the original situation, it was 2 times the gap. So the wavelength now is 1/3 of what it originally was, which means the frequency of this third mode is 3 times what it originally was, or 23.7 hertz. And you could continue that mathematical pattern for higher and higher modes of oscillation. Problem 6 was talking about the speed of a standing wave. A string fixed at both ends is 8.4 meters long and has a mass of 0.12 kilograms. It's subject to a tension of 96 newtons and then set oscillating. What is the speed of waves on the string? What's the longest possible wavelength for a standing wave? And what is the frequency of that wave? Well, let's take those on in the order given. Wave speed, depending on the physical characteristics of the system, is the square root of tension over the mass density. So that's 96 newtons divided by, let's see, mass, 0.12 kilograms, length, 8.4 meters. And if you do that and calculate that, you get just under 82 meters per second. That's how fast the wave's traveling back and forth along the string. We want to know the longest possible wavelength for a standing wave. Well, if you have the string fixed at both ends, again, the longest possible wavelength is you take that fundamental mode of oscillation that looks something like this, and that represents 1/2 a wavelength. You got to stretch it imaginarily over here to get the full wavelength of that wave, which means in this case the wavelength is equal to 2 times the length of this gap if this gap is some distance L. And that means the wavelength of this mode is 2 times the 8.4 meters, and that is 16.8 meters. Finally, what is the frequency of this wave? Well, here we use our relationship between speed, frequency, and wavelength to say that frequency is equal to wave speed divided by wavelength. So that is 81.98 meters per second divided by 16.8 meters, and that is 4.88 hertz. The final problem that we looked at was put on here for a couple of reasons. Number one, to point out that waves, electromagnetic waves, which we'll be transitioning into studying shortly when we talk about light, all travel at the speed of light, and to also give some more practice in applying our physics 1 ideas, which are basically all you need to solve the problems in here. Light in space. How long does it take a radio signal to travel 150 kilometers from a transmitter to a receiving antenna? Well, speed is distance over time. That means time is distance over speed. And in all of these problems, the speed of light is taken to be a constant. It's pretty fast, 3 times 10 to the 8th meters per second. So if I plug in my distance, this is 150 times 10 to the 3rd, if I'm converting that to meters. If I divide that by 3 times 10 to the 8th meters per second, I find a time of about half a millisecond. So it doesn't travel instantaneously, but in the scale of things that we are keeping track of, that's pretty quick on the human scale there, 0.5 milliseconds. We see a full moon by reflected sunlight. How much earlier did the light that enters our eye leave the sun? We have the Earth, Moon, and the Earth-Sun distances given to us. So broadly, we got the sun. Looks exactly like that. We're over here on Earth. We are giants. We're standing here. The moon is over here. So we're talking about light traveling from the sun to the moon and then being reflected into our eyes. So again, the time interval for that would be the distance over the speed. Well, the distance is going to be the Earth-Moon distance. That's one part of the path. I'm going to put the Earth-Sun distance first, actually. 1.5 times 10 to the 8th kilometers is going to be 1.5 times 10 to the 11th meters. Moon to me is 3.8 times 10 to the 5th kilometers, so that's 10 to the 8th meters. And the speed is the speed of light, 3 times 10 to the 8th meters per second. Now, you could point out that there's going to be slight variations here, right? If the moon's on the far side of the Earth, then I've got to travel the sun-Earth distance, and then the Earth-Moon distance, and then back the Earth-Moon distance. If the moon's directly overhead, it's kind of like we've set up here. If the moon is slightly closer to the sun and we're viewing the backside of it, or just the sliver of the moonlight there, it might be this minus this. But notice this is 3 orders of magnitude smaller than this. This is going to be a small correction on our result, actually. If you set it up the way that I set it up, it calculates out to be about 501 seconds, and that is just over 8 minutes. What is the round-trip travel time for light between Earth and a spaceship orbiting Saturn, which is 1.3 times 10 to the 9th kilometers distant? Well, round-trip travel time would suggest that, okay, I'm here orbiting Saturn, I want to send a signal back to Earth and then get a reply back. So how much time would that all take? Meaning I need to go 2 times this distance. So that time, once again, is a distance divided by a speed. So it's going to be 2 times 1.3 times 10 to the 12th meters divided by 3 times 10 to the 8th meters per second. And that ends up being about 8.67 times 10 to the third seconds. So now we're getting a little bit long here. That's about 144 minutes, which then is about, what, 2.5 hours? Yeah. So whenever you're next orbiting Saturn, don't expect an instantaneous reply from NASA. Finally, the Crab Nebula, which is about 6,500 light years distance, is thought to be the result of a supernova explosion recorded by Chinese astronomers in AD 1054. In approximately what year did the explosion actually occur? Well, a light year, if you are unfamiliar, is the distance that light travels in 1 year, which means if it is 6,500 light years distance, then the time is actually 6,500 years, because that light travels at, unsurprisingly, the speed of light. When did this explosion actually occur? So if we're here on a timeline at AD 1054, when the Chinese astronomers saw that, this thing had to have happened 6,500 years before that in order to give enough time for the light to get here. So if you travel back past zero, you are going to arrive at a time that is 5446 BCE. And I see my work is entirely off the screen there, so I will slide down. So the time, 6,500 years, and then 1054 all the way back to 5446 before the Common Era would be the time when the supernova happened 6,500 light years away. So those are the problems we looked at in dealing with waves in class, and hopefully this sets you up for working on the problems on the waves problem set. As always, if you've noticed any errors in my solutions, I'd appreciate you letting me know that. Thank you.